Okay. So we will speak about constraint satisfaction problem today. Just a quick picture of me, so you know who am I. I will switch it off because the bandwidth. Okay, constraint satisfaction problem. As usually with my lectures, I will introduce first the basic definitions, and then I will go through the algorithms that can be used for solutions. And we will start with from the very general approach, and let's say going to the kind of very sophisticated algorithms. So from the methodology point of view, constraint satisfaction problem deals with possible words and constraints. Each word is expressed in terms of variables and their domains. In other words, each word is can be represented as a set of variables, and each variable has its let's say values that can be assigned to that variable. Furthermore, we specify constraints that represent somehow the real world problems. And the goal is to find a possible word that, by assignment of values to variables, you can find the word that satisfies all sets, all constraints. And as an example, classical one are map coloring, how to assign colors to countries in such a way that no neighboring states share the same color, or queen problem, when you need to place queens in such a way that none of them is in the danger of the other, or maybe quite let's say favor the puzzle Sudoku. So let me specify that formally. Constraint satisfaction problem is basically a finite set V of variables labeled as a Vi for I equal from 1 to n. That means we have n variables. Each variable can be assigned with a specific set of possible values, and that set is called domain, and it is non-empty. Domain di for variable Vi. And we have a set of constraints C1 till Cm, and each constraint uses a subset of variables to describe limitations for values of those variables. Let me make an example, very simple one. We have a problem containing just one variable, V1, and its domain is basically R values 1, 2, 3, 4. We have two constraints, C1 and C2. C1 basically saying that value of variable V1 cannot be 2, and C2 saying V1 value must be higher than 1. More, let's say, complex problem is to have constraint satisfaction problem with two variables, V1 and V2. The domain of the first variable is 1, 2, 3, and domain of the second variable is just 1, 2. And we have three constraints. Constraint 1 saying, okay, it cannot be 2. C2, V1 plus V2 must be less than 5, and constraint 3, v1 must be greater than v2. A model. We basically search for assignment of values to those variables. And if we find such values, such assignment of all values that satisfies all of its constraints, then we got a model. That means a model is a possible word that satisfies all constraints. If we have that first example, one model is, for example, to assign 3 to v1 because it satisfies, it belongs to the domain, the value, and it is not equal to, and it is higher than 1, and the same is valid for v1 is equal 4. Sometimes we speak about so-called CSP solution. In this example, using two variables, we have several possible words. Here, basically 6 of them. However, only 2 of them are models. For example, the first constraint violates the first model violates the third constraint, that v1 is not greater than v2. And here we have a model. As you can see, v2 is not equal to the sum is 3, which is less than 5, and v1 value is higher than v2 value. I will present and demonstrate some examples and algorithm using this map coloring problem. When we have a map of Australia and its countries, Western Australia, Northern Territory, South Australia, Queensland, New South Wales, Victoria, and Tasmania. We will basically short their names to be WA and TQ, NSW, V, SA, and T. We can color this map using 3 colors, red, green, and blue. That means all these variables has the same domain, values these 3 colors. And the constraints are quite easy to specify. Basically, any adjacent regions must have different colors. You can specify that in such a way that WA is not equal to T if the language allows that, or the other way is that the tuple VWA and T is basically one of the element from this set, and you basically name all possible configuration of colors. Here is one of the solution. That means a model, and basically here is, as we can represent it, here is basically the schematic let's say description of the model, in which we basically say that WA variable is assigned to red, and so on. Constraints. Constraints are restrictions on the values, and basically we can distinguish so-called unary constraint, that is a restriction involving just a single variable. For example, variable v2 is not equal a value 2. Generally, if we have a restriction operating on k different variables, then we speak about k-array constraints, and we have specific names for some of them, like, for example, binary, that means k is equal to, and for example, it is like v1 plus v2 is less than 5, or ternary, like, for example, with 3 variables, v1 plus v2 plus v4 is less than 5. Usually, it is quite often case that we deal only with binary constraints. That means where k is equal to. The constraints can be specified by generally 2 possible ways. You can either list all combinations of valid domain values for the variables constraint, let's say, participating in the given constraint. For example, if we have a binary constraint v1 is greater than v2, and the domain of variable v1 is 1, 2, 3, and domain of variable v2 is 1, 2, then basically the constraint, this one, can be expressed as a set containing just these 3 items, these 3 tuples, 2, 1, 3, 1, 3, 2, which basically are all possible combinations which satisfies this relation. It is also possible to create a function predicate that returns a true value if the provided values for each variable satisfies the constraints, let's say, implementing by the function or not. Okay, what is the scope of constraint? As you could notice, each constraint can be expressed as a pair, so-called scope and relation. Relation is basically that list of allowed combination of variable values. For example, like those here, 2, 1, 3, 1, 3, 2. That's the relation. And the scope is basically a set containing those variables that are involved in that constraint. So, for example, for v2 is not equal to, that constraint has a scope v2, just one variable. This v1 is greater than v2, has scope these 2 variables. And here we have a ternary constraint, that means which has scope v1, v2, and v4. The quite easy question is how many variables are in the scope of the k-array constraint. Of course, I think that everybody can estimate that it is a k variables. That is a scope. Furthermore, it is obvious that this constraint satisfaction problem can be quite general, and the domains can be anything. So it is quite good to select subproblems. For example, so-called a finite constraint satisfaction problem, in the short CSP, that uses a finite set of variables and also a finite domain for each variable. That means we have a finite set of variables and finite values, a finite number of values for each variable. In the next, let's say in our lecture, we will study only those finite CSPs. However, you should know that basically there are a number of other techniques that operate with infinite domains and continuous domains and so on. Although I will speak about CSP, basically it means that FCSP. The scope E of each constraint in such FCSP is automatically finite because any subset of finite set of variables is finite. Okay, now we defined the problem of the CSP, and there are a number of possible ways of goals that can be achieved. The first of all, we can ask this question if such a model exists or not. Just the question, we don't deal with the actual form of the model, just about its existence. Or we can search for a model. We are not interested, let's say, about others, but it is enough to know just one model. Or we can search for all models, all possible models. In some cases, we don't need to know all models, but we operate only on that we know the count, the number of the models. In some cases, there are additional constraints that doesn't need to be, let's say, satisfied, and they only express the model quality. And in that way, we search for so-called the best model. And we deal in such a case with an optimization problem. In some cases, if we know the set of all models, we can ask if there is a specific property that is held, let's say, in all models. So it is a kind of basically another formula that is satisfied in all models. How to tackle the solution? For such approach, we define so-called state. And the state is an assignment of values to some or all variables. That means we assign some values to the variables, possibly not to all of them, and such an assignment is a state. And that can be complete, when every variable has a value, or it can be partial, when some variables have no values assigned so far. We also speak about so-called consistent assignment, and that is such an assignment that does not violate the constraints. And it can be also partial or complete. And a solution to a CSP is a complete and consistent assignment. And as I mentioned, in some CSPs, we can maximize an objective function, and that leads to constraints optimization problems. Or we can have a so-called soft constraints, so-called preferences, and they basically somehow relate the problem to the cost, and again they lead to the constraint optimization problems. It can be shown that even the simplest problem of determining whether or not a model exists the first question in a general CSP with a finite domain is NP hard. In other words, there is no known algorithm with the worst case polynomial runtime. And there is no hope to find an algorithm that is polynomial for all CSPs. On the other side, we can find very efficient polynomial consistency algorithms that are able to reduce the size of the search space, and you will see them later on. And that can be used in the practice. Also, there are some algorithms that are very efficient in special cases. Or it is possible to use approximation algorithms that are able to find a good solution very quickly. Even if you analyze them from the theoretical scientific point of view, there are no guarantees that the solution will be found. A majority of algorithm works very fast on typical, that means typical cases, that means not worst cases. From the mathematical point of view, mathematician can find the worst case in which basically these algorithms don't work. Furthermore, constraints can be expressed using graphs. If each constraint relates at most two variables, then we speak about a binary CSP. For such a CSP, we can constrain so-called constraint graph, where variables are nodes, represented by nodes, and arcs represent binary constraints. Like here, for example, you can immediately say that there is a one constraint between V1 to V3, between V1 to V2, no constraint between V1 and V5, and so on. Why it is important to have such a representation? Because if you analyze the structure of such a graph, that structure can help you to find efficiently the solution. For example, as you can see here, this separation means that this problem can be divided into two subproblems, and they can be solved independently. In other words, such a graph can be used to simplify the search for the solution. Is it used in the, let's say, real world? Of course, on every basically industrial problems, you can find such problems. For example, assignment problems, who teaches what class, timetabling problems, which class is offered when and where. It is the same for hardware configuration issues, hardware verification. For example, IBM uses many times in its systems. You can schedule the transportations. You can schedule factories, floor workshop planning. And of course, it can be used for number of puzzle solving, like crosswords, Sudoku, and so on. It can be, if the software is not big, a really large one, so that means the kind of small to medium programs, then it can be used also for software verifications. Personally, I participated in, it was like 15 years ago, in Oracle Automation on the project that in which we helped to solve these issues for Boeing company, and the issue was that if anything happens in the aircraft, they need to find quickly, let's say, where is the problem, and it can be redefined as a constraint satisfaction problem with a huge number of variables, like millions of variables. I will show some examples on this quite easy problem. It is called so-called 4 queens, that is viewed as a CSP, and assume that 1 queen is in each column, and the question is how to place the queens in such a way that they don't attack each other. This CSP can be described using 4 variables. That means placement of the queen in what row. And we have 4 rows. That means the domains of those variables are 1, 2, 3. And the constraints are 2. Basically, the 2 types, that 2 queens cannot be in the same row. That means Q1, Qi is not equal Qj. And also, they cannot be on the same diagonal. That can be expressed that the difference between the rows must be different from, let's say, their columns indexes, the difference of the column indexes. Of course, again, these constraints can be translated into the set of, let's say, allowable values, like, for example, for values Q1, Q2, we have this list of possible combinations of rows. And here is the question to you. If we have such a n queens problem, that means instead of 4 queens, we have just basically n, the arbitrary number. And I ask you, what order of magnitude n can be practically solved for n queens problem? We will see that later on, but let's say to test yourself, what is your, let's say, expectation. So I will run all. Okay. So you can answer that. So the answers are 30 queens, 10 up to 1,000 queens, 10 millions queens, and 1,000 queens. So we have let me wait for a couple of seconds more. So we have 7 remaining to show. It does not change. Okay, let me show the results. For A, 6 of you. For B, 2 of you. C, just 1. And D, 9 of you. Basically, majority thinks not quite small, but let's say just 1,000 queens. You will see that I will present you with the algorithm that is able to operate with 10 millions of queens. So if it is done cleverly, you are able to operate with, let's say, millions of variables. And it is not like in the previous let's say, lecture with the planning that we were able to operate with let's say, much higher number of states. Here we have a 10, let's say, about from 10 to 100 millions of variables. Okay, just one of you selected that correctly. Okay, let's continue. Thank you for your response. We deal with the algorithms. So just quickly through the very general one that is called generate and test. In fact, this is the classical approach in artificial intelligence. If you don't know anything else, you can always to start that you generate everything possible and to search for the right solution. And we know everybody that it does not work quite nicely, but it is a kind of baseline solution. In other words, you create a cross product of all domains. You create every possible combination of values for all those variables, and then accessing each configuration one at a time, you test the constraint if all constraints are satisfied. If not, you continue and generate and you continue in the generation. So kind of code for just three variables would can look like for A in domain of A, for B in domain of B, and for C value in domain of C variable. If that variable, let's say, if are assigned to these values, then check all constraints. If it is satisfied, return the solution. If not, you continue in that in those loops. In Python, instead of just let's say going through a huge number of for loops, you can generate those combination using, for example, generator functions. There is another way how to do that. You can do that incrementally. So in this case, you start with a kind of dump approach that starts with just let's say kind of initial solution, and you try to fix it in such a way that after several steps you get to the let's say solution. So the initial state, for example, can be an empty assignment, and then in the next step, which is called a successor function, you take an unassigned variable, you select its value from its domain, you select such a value that is does not conflict with let's say with the current assignment. That means the constraints are satisfied, and you loop through this successor function, assigning other values. If there are no legal assignments, basically you fail and you continue in other way. If current assignment is complete, then you got the solution. Nice thing is that this procedure is the same for all CSPs. However, you can imagine that as if you have a tree, you start from the node, and you select the variable, and then assigning the value, you continue to another variable, and if it fails, you continue with another assignment, and so on. And basically, it looks like a tree, and in every node, you select one of the variables and, of course, one of its values. So you can imagine that you search through the tree and using depth-first search, and at each level, you have, for example, in the depth L, you know that L variables are assigned, and you still need to select one of the remaining n minus L variables. And assuming that the domain is basically the same, containing D values, you have a, let's say, branching factor n minus L multiplied by D possible values. If you do that, let's say, in the consistent way, you end up with a tree that is n factorial D up to n having this number of leaves. This is really a huge number. So the first thing is that you can immediately notice that variable assignments are commutative. In other words, you can assign first WA from that map coloring problem, that Western Australia is red, then Northern Territory is green, or you can basically achieve the same results using the steps that you assigned first and green to North Territory and then red to WA. Because of this commutative feature, we don't need to select variables at each node. You basically select just one variable. So instead of having that n minus L variable selection, we have just one. And a branching factor is D. So in this case, we deal only with a, well, only, it is still quite large, D up to n leaves. Really a huge number of leaves. And if you do this, that means depth-first search with a single variable assignment at each node, we call that approach a backtracking search. And it is a kind of basic uninformed algorithm for a CSP. And in this case, if you try that, you can solve the n-queen problem up to, let's say, 25. And so pseudocode could look like this. So basically, we perform backtracking search, and it basically calls the recursive function with an empty assignment and a list of constraints. And that function, recursive backtracking, checks first if the assignment is complete. Then basically we return the solution. If not, we select, let's say, one of the unassigned variable. And for each value of its domain, we check if that value is consistent with the assignment, basically given constraints in that CSP description. If it is consistent, then we add that pair variable and its value to the assignment, and we call the next level of this function. If the result returned is different from failure, then we return the result. If it is failure, then we know that this pair does not lead to the solution. We remove it from the assignment and we continue with the next value in that domain. If everything fails, then we return failure. This should be slightly put to the left. So this is a backtracking search. Example demonstration is like in the coloring problem. We basically assign the colors, and in the depth first search, you continue with the assignment and so on, and you try to find the appropriate solution. Now, if we have such an approach, the backtracking search, we can gain in speed in many times, let's say kind of heuristics, or let's say improvements. First, we can ask which variable should be assigned next. Also, the values can be assigned in a specific order. Which one should be used? Another question is, if we analyze a solution, let's say the partial assignment, at a specific level, can we detect inevitable failure much earlier than really to find the constraint that it is not satisfied? Furthermore, can we take advantage of the problem structure? So in fact, if we know the graph of these constraints and so on, is it possible to arrange the algorithm in such a way that we can speed up it? And that's exactly what I will do in the next steps. And as basically, I will continue with step by step using these, let's say, suggestions. So the first is how to assign, how to select variables and its values. The first heuristics for selection of variables is this one. It is called minimum remaining values. Basically, it says choose that variable with the fewest legal values. For example, having this, let's say we select this country, then we can select either this or this. So basically the green one, and as you can see, the blue has basically only one value, legal value that is remaining. So that variable is selected as the next one. If we have a number of possibilities how to select the variable, like in this first two selection, we can use another heuristics that is called degree heuristic. Choose such a variable with the most constraints on the remaining variables. In other words, if the first heuristics produce several variables, then we can select a variable that that is basically involved in the most constraints on the remaining variables. In other words, for example, in this case, it is just the blue because it has a relation with each other variables. If we selected blue, that means the remaining is each variable is basically dealing with here 2, here 1, 2, 2, and 1. So basically we can select one of these threes. We selected the green one, and now let's say the obvious case is that the red is selected because it has another constraint with empty, let's say with not assigned variable. So that was assigning variables. How to select a variable. The next step is how to select its values. And the heuristic is called least constraining value. In other words, choose the least constraining values. For example, having these steps, at this step, you can select for the SA. Sorry, you can select for Queensland. Q is this country, either red or blue. If you select blue, that means for this region, which is SA, South Australia, you have no other choice. You have no remaining values. While if you select red, you have still one value for SA. So this is selected because it rules out the fewest values in the remaining variables. If you use so far presented heuristics, you can solve, let's say, up to 1,000 queens problem. So we have variables order, values order. Now, what we can do next? Forward checking. Basically, it means that you try to detect earlier the failure. And you do that in such a way that you try to, let's say, maintain remaining legal values of unassigned variables. And if you find a variable that has no legal value, then you know that whatever you do, you always end up with a failure. So you can just fail and let's say backtrack back. So having this case, for each state we have 3 possible values of colors, and if we assign red to WA, West Australia, then here we have a North Territory, and here is a South Australia, and it cannot they cannot use red anymore. So we drop that red here and red here. Can we propagate it further? Yes. If we assign in the next step green to Queensland, then NT cannot use green anymore, and also SA cannot use green anymore, and the same is for New South Wales here that cannot use green. Now imagine here we have a NT just with the remaining blue and SA with the remaining blue, and they are neighboring states, neighboring regions. So in the next step, basically, if we either assign V to blue, SA is empty, and we cannot. We know that we don't need to continue because all possible, any kind of assignment leads to failure. That was forward checking. You basically check if you make an assignment, you drop those values from the neighboring in such a way that you can that there are only legal values. Another approach is based on the node consistency, or so-called R consistency, or even, let's say, generally path consistency. Yeah, let's say forward checking propagates the information from assigned to unassigned variables, but actually it does not provide early detection for all failures. And as I mentioned a bit earlier, if you check that NT and SA here is blue, they cannot be blue by constraint. So you are able to detect that even this case is leading to failure. So using constraint propagation, that means checking checking combinations of remaining values, you can detect failure earlier. How to do that? For example, using R consistency, you check if so-called X is consistent with Y if for every value X from X here, there is a sum allowed Y for the variable Y. In other words, for example, in this situation, WA is assigned red, queen to green. You, by forward checking, you drop those remaining values, and now you can check if SA is is blue, then and SA is here, and NSW is here, neighboring, then NSW can be red. Okay, so basically for blue, for SA, there is a red for NSW. If you do it in the opposite way, red allows blue, okay, but if you assign blue to NSW, then you have a no remaining value for SA. So this value must be dropped. Now, if you drop the blue and you have a NSW and Victoria, neighboring states, then checking these values, Victoria, if it is green and as red, it is okay, but if it is red, we have no remaining value in here for NSW, and therefore red cannot be assigned to V. If any variable loses its value, we need to check all neighbors of X, that means all constraints dealing with X, to check them again, let's say, if such situation is not, let's say, it does not occur. In other words, first we drop the, let's say, the blue from NSW because we change the domain of this. We need to check all, let's say, constraints dealing with NSW, and we can find that if we apply, let's say, those constraints with a V, that here again we can drop one of the value of V. Finally, we can find that if SA is equal blue and T, because it is a South Australia and Northern Territory, these two states cannot be blue as well. So we need to drop blue for SA, and we know that there are no legal values and it is a failure. So basically we can immediately return back. So even, let's say, we were just here at this state, by forward checking and following by our consistency checking, we are able to find that such a configuration leads to failure, and we don't need to continue with, let's say, to check all possible combinations of these assignments of the remaining values of for the remaining states. These R consistency can be used for early detection of the failure. The failures are detected, let's say, earlier than with forward checking, and it can be also run as a preprocessor or after each assignment. The pseudocode for this algorithm is quite, again, easy. It is called AC -3. So we have a queue. We have a queue of what should be checked, what variables pairs should be checked. You take the first from the queue. You check if it is if you need to remove some values. If yes, that means if you need to remove, that means it is a true, and you need to recheck all neighbors. That means you basically add those pairs, the neighbors to xi to the queue, and you solve it, let's say, in the loop. And that remove inconsistent values, basically you first to state that you didn't remove anything. Then for all variables, for all values in the domain of variable xi, you check if there is no value I for the other variable xj, that basically under the condition that you try to satisfy the all constraints between these two variables, and if there is no such value in the other variable xj, then you need to delete that x from the first variable xi. You set that you remove something, and you repeat that for all values, and then finally you return the status if you delete it or not, because you need basically to propagate it forward. In this case, the complexity of the problem is n squared d cubed. In some special cases, it can be reduced to n squared d squared. Okay. Now we are approaching solutions dealing with a structure. So far, we are able to order the variables, order their values, assignments. Then, based on the level, we can do forward checking. In other words, propagation of the constraints, and we can also check consistency regarding the constraints. Now, how to deal with the structure of the problem? If we express the map of the Australia as a graph, we get as a constraint graph, we get this graph. we can immediately say that Tasmania and mainland are independent subproblems. We can solve, let's say, independently this Tasmania and the rest of states. So the first thing is that basically to check if there are some connected components, and then deal with each component as a standalone problem. Let's make some let's say properties of this approach. If we have several subproblems, each having C variables, and we have a total variables n, okay? So each independent problem is C variables from n. So we have n divided by C subproblems. And each of which takes at most d up to c were to solve, as we saw earlier. So we have a n divided by c times by dc. And as you can see here, it is linear in n. So if, of course, this constant can be quite high, but let's say it is linear. In other words, quick, let's say calculations. If we have 80 variables, each having two values, d is equal to, and we can divide it to 4 subproblems, each having 20 variables, then using the original approach, d up to 80, we would solve that problem in 4 billion years, assuming that we have a hardware able to performing 10 million nodes checking per second. If we are able to divide it in this way, then we have 4 problems, each having complexity 2 up to 20, and we deal just with a 0.4 seconds at the same speed. This is a huge difference, I believe. So this is the how we can tackle those huge problems. The question is, are we able to divide a problem, CSP, into independent subproblems? Well, in some cases, it's quite easy. For example, for tree-structured CSPs. In other words, if we make constraint graph, it looks like a tree. So basically, we have n variables represented as n nodes, and as a tree property, we have just n minus 1 arcs between those nodes. And I will show you in the next slide that using directed arc consistent way, we are able to solve it in basically in linear time, or let's say this kind of time. This is how to transform the graph, such a graph, to the basically linear linear sequence. And each step basically in each step you need to compare domains values of two variables. So if the constraint graph has no loops, then basically we have this complexity time n multiplied by d cubed. D squared. This is, of course, very nice time compared to general worst case time d up to n. And in many times, this feature can be observed, this kind of tree-like structure can be observed in a logical and probabilistic reasoning. And that's basically what they exploit in their, let's say, fast solution. So how it is actually done? Well, first, you perform a topological search. You select one variable as the root, and then all the variables in the sequence in such a way that every node's parent precedes the actual node in that ordering. In other words, A is root, then we select B. Now we can place here the C as a next step, followed by the D, and again here we can select either E or F to be in the next step, but the sequence can look like this. So, and this can be done in that linear time, topological sort. Then going in the backward way in that sequence, so basically from n to 2, you apply that remove inconsistent function between the node and its parent. To basically you restrict parent values based on the given variable here. In this way, you propagate the information up to the root, and then in the following step, you are able to go in the opposite direction, basically from 1 to n, and assign each node consistently with the parent. So at first you assign A, you select any kind of remaining legal values, then assign B based on the selection of A value, C based on the selection of B, and so on. So very nice approach. Now what this is a nice approach, but assuming tree-like constraint graph. What to do if we have a graph like this, which is not definitely a tree? Well, what we can do is we can select a variable, such here as A, and assign a given value. Based on this value, we can propagate this constraint of this value to the rest of the nodes. And then basically we can drop the node. And if we do that in the, let's say, a proper way, we can transform using, let's say, by dropping of these nodes, the problem to the tree, which is here. Of course, the question is how to find those nodes that after their removal we produce the tree, and it is so-called cut set conditioning. So basically, you are trying to search for a set of variables that if you remove them, you get a tree. And if the cut set is size C, that means you remove C variables. That means you know that you need to check the up to C configurations of the cut set variables, and each remaining task is having complexity n minus c remaining variables and d up to d squared, let's say, because it is that only comparison of two variables in each time. So again, for small c, if you are able to select a minimum number of these variables, this is quite good runtime. Okay, and the last method I will present is so-called hill climbing work or iterative algorithms belonging to the iterative algorithms for CSPs. And basically, it is a kind of like hill climbing, simulating annealing, working on complete states. That means all variables are assigned. Of course, at the beginning, you don't know exactly how to assign properly those values. So you need to allow states with n satisfied constraints. Some constraints are broken and you need to fix them. And that's exactly what the operator reassignment performs. That it tries to reassign values in such a way that the number of broken constraints are minimized. The variable that can be reassigned can be either selected randomly from the set of conflicted variables, that means that causes any unsatisfied constraint, or there is also a heuristic, so-called min conflicts, and basically you choose a value of the variable that violates the fewest constraints. And as a heuristic, you use hn function that calculates how many constraints are violated. For example, for the 4 queens problem, you have 4 queens in 4 columns. That means initially 4 up to 4, 256 states. And you can move a queen in a column. The goal test is that no queen is attacked by another queen. And Hn here is basically the calculation of the count of the number of attacks. So here we generated just an initial assignment. And as you can calculate, we have 1, 2, 3, 4, 5, 5 attacks. So you can select any queen or the queen that has that produces this violates the fewest constraints, which turn up to be this this one. And you move it, you assign a value, and the number of attacks is here 2. If you select this queen that let's say that causes the attacks, that means you can move it again to the legal value, which is here, and you are done. You have a solution. Using this approach, although it looks like quite weird because you don't explore any kind of structure and so on, it is very efficient method, and it can be shown that you are able to solve the n queen problem with those 10 million queens, and roughly in 50 steps usually it is solved. It looks that this approach is able to tackle any randomly generated CSP except some range where if the number of constraints is about this, let's say, creates a specific ratio to a number of variables, then this method has a rather so-called critical ratio that causes that the CPU time is much higher than it is expected in the rest of the problems. So it works mostly, but in some cases it fails. So from summary point of view, constraint satisfaction problems are a special kind of problem. We have variables, we have values, and we have, let's say, a kind of state that describe the assignments of values to variables. And the goal is to find such assignment that satisfies all constraints given to variable values. The basic solution is just the backtracking. When we perform depth search, and in every step we assign one variable in the node with selected value, and there might be some speedups based on ordering of variables and how values are selected, let's say the order of values. Also, we can use techniques so-called forward checking when we propagate assignments further and to find, let's say, failures earlier. And if we perform also arc consistency propagation, then we can even earlier detect, let's say, the failures even earlier than with the forward checking. And if we are able to explore the structure of the problem, for example, like if we are able to convert the CSP to the tree-like structure, then we can solve such problems in linear time or in, let's say, near linear time, let's say, cases. And it should be let's say, noted that iterative min conflicts approach is usually very effective in practice. And that's everything from my point of view. We have still some time for questions. So are there any questions?
Thank you, Ratko. Thank you very much.
It seems that everything is so obvious that they will solve the assignment in the lab quite easily.
Hopefully.
Well, it seems that everything is clear. So I am stopping the recording.